Hi, and welcome to Dr. V's AP Chemistry webcast. Today we're going to talk about oxidation and reduction. These are fundamental ideas that really build out the entire electrochemistry unit, which is a big topic in AP Chemistry. Here's what I'd like to accomplish in this webcast today. First, I want to talk about oxidation and reduction and define the terms and compare them so that you know what they mean. And then we're going to go on and talk about half reactions to represent oxidation and reduction processes. You need to be able to recognize these. And then we're going to compare redox and non-redox reactions. I will say, if you don't know how to assign oxidation numbers, you really want to go back and review that and watch that webcast before you continue with this one. Let's start by defining the term oxidation. The modern definition of oxidation talks about it being a loss of electrons. If a species loses electrons, we say it gets oxidized. What we'll see in oxidation is the oxidation number of the species that loses an electron, or more than one electron, will go up. So for example, let's say we have a sodium atom, and this sodium atom loses an electron to form a sodium ion. That's an oxidation process. The electron was lost. We can represent this oxidation process with a half reaction. We're calling it a half reaction because it's only half of the story. So let's think about that sodium atom losing an electron. So we have a sodium atom as a reactant, we have a sodium ion as a product, and we lose an electron. So this is an oxidation half reaction. So we can think of the electron as a product. That's a hallmark of an oxidation half reaction. The other thing I want to point out about an oxidation half reaction is that the oxidation number goes up. It goes from 0 for the sodium atom on the reactant side to +1 for the sodium ion that we make. So this is an oxidation half reaction. An important thing I want to note about this half reaction, look at the sum of the charges on both sides. The sodium atom on the reactant side has a charge of 0. The sum of the sodium ion charge and the electron charge is also 0. So the half reaction shows conservation of mass, and it also shows conservation of charge. And this is an important thing when you write an oxidation half reaction. The sum of the charges should be the same on both sides, and you have to have conservation of mass. Let's look at another half reaction. Let's say we have a lead-2 ion. It can lose 2 electrons and form a lead-4 ion. So it's an oxidation half reaction because the oxidation number goes from +2 for the lead ion to +4 for the product lead ion. And then I lose 2 electrons. So those 2 electrons are the product, and this is an oxidation half reaction. Now let's consider a reduction process. Reduction is defined as a gain of electrons. So if a species is taking on electrons from outside, we say it's reduced. Now this is a little counterintuitive because when we think of reduction, we think of losing things, and we're gaining electrons. So that term seems a little non-intuitive sometimes to students. What we have to remember is that the oxidation number is going down in reduction because we're gaining electrons, and electrons have a negative charge. So the charge of the species is going to go down, or the oxidation number of that species is going to decrease. That's what's reduced in reduction. Let's think about reduction a little bit more. Let's say we have an iron 3 ion, and it can undergo reduction by gaining 3 electrons. And when it undergoes this reduction process, it makes an iron atom. So it's reduction because it went from iron 3+ to iron with a charge of 0. How do we represent this as a half reaction? So we had Fe3+ gaining 3 electrons to make iron atoms. So I'm going from an iron ion with a charge of +3 to neutral iron atoms with a charge of 0. So the oxidation number went down, so that's one way of recognizing that this is a reduction half reaction. The other way to notice that it's a reduction half reaction is that the electrons are reactants. They're on the left-hand side of the arrow, so that's the other hallmark of a reduction half reaction. Let's look at another reduction half reaction. This one is elemental fluorine undergoing reduction to form fluoride ions. Again, we're showing conservation of mass and charge with both of our reduction half reactions. The sum of the charges is the same on both sides of each half reaction. So with fluorine, we've got 2 fluorine atoms in the fluorine molecule, each gaining 1 electron to make 2 fluoride ions. So I have 2 fluorine atoms on the left, I have 2 fluoride ions on the right. I need 2 electrons to make this process occur. So the sum of the charges has to be the same to show conservation of charge. And I've got electrons as the reactant. The oxidation number of the fluorine on the left is 0. The oxidation number of the fluoride ions on the right is -1. This is a reduction half reaction. Sometimes it's hard to keep the definitions of oxidation and reduction straight, and there are some mnemonics that can be really helpful here. The first mnemonic is Leo the lion says grr. Loss of electrons is oxidation. Gain of electrons is reduction. If that helps you remember the definitions, then use it. The other well-known mnemonic for oxidation and reduction is oil rig. Oxidation is loss. Reduction is gain. When I teach these units, I say these mnemonics to myself multiple times a day. Now that we know what oxidation involves and what reduction involves, let's talk about redox reactions. We can't have oxidation without reduction. You can't lose electrons without something gaining electrons. They both go together. So we talk about oxidation half reactions and reduction half reactions, but they do happen together. So they're oxidation reduction reactions, or for short, redox. One of the things that has to be true with a redox reaction is that the total number of electrons lost in the oxidation half reaction have to equal the total number of electrons gained in the reduction half reaction. So when we go to balance these equations, we do have to make sure that ultimately charge is conserved. And so we have to sometimes multiply one of the half reactions by some factor. The other thing to note in a redox reaction is that oxidation numbers of species will change. One species oxidation number is going to go up because it got oxidized, and another species oxidation number is going to go down because it gets reduced. And so we can use that to determine whether a particular reaction is a redox reaction or not. In order to do that successfully, you do have to know how to assign oxidation numbers, and that might be worth reviewing if you're not 100% confident with those rules. Let's look at a few reactions and decide if they're redox or not redox reactions. So I'll show the equation. I want you to pause the video, decide for yourself if you think it's redox or not, and then listen to my reasoning. Here's our first reaction. CuO plus H2 makes copper metal and water. Let's look at all the oxidation numbers. Copper starts at +2 and ends at 0. The oxygen stays at -2 on both sides. The hydrogen goes from 0 to +1. So yes, this is a redox reaction. H2SO4 reacts with sodium hydroxide to make sodium sulfate and water. Is this a redox reaction? What do you think? Let's put in all the oxidation numbers, and if we compare, hydrogen is +1 on both sides. Sulfur is +6 on both sides. Oxygen is -2 on both sides. Sodium is +1 on both sides. Nobody changed oxidation numbers, and therefore this is not a redox reaction. How about magnesium carbonate decomposing to make magnesium oxide and carbon dioxide? If we assign oxidation numbers, magnesium's +2 on both sides, carbon's +4 on both sides, each oxygen is -2 on both sides. This is not a redox reaction. Some decomposition reactions are redox reactions, but not this one. What about the reaction of diiodine pentoxide reacting with carbon monoxide to make molecular iodine and carbon dioxide gas? Let's assign oxidation numbers. Iodine starts at +5 on the reactant side, ends at 0 on the product side. Oxygen is -2 for all the species, but the carbon is +2 in the carbon monoxide and +4 in carbon dioxide. This is a redox reaction. What about this synthesis reaction? I have elemental phosphorus reacting with elemental sulfur to make diphosphorus pentasulfide. Well, elements always have an oxidation number of 0, but they're not 0 in the compound. So this is a redox reaction. In fact, that can be a handy trick. Any reaction that has an element as a reactant or a product, like this last one, or the I2O5 plus CO reaction, which has I2 as a product, anything with an element will be a redox reaction. I'd like to switch gears a little bit and look at a balanced redox reaction and determine what's oxidized and what's reduced. Try it on your own first, and then listen to my explanation. We'll start by assigning oxidation numbers. Elemental sodium is 0. Elemental bromine has an oxidation number of 0. Sodium in sodium bromide is +1, and the bromide in sodium bromide is -1. Clearly, things are changing. One thing I do want to emphasize is that when you're asked what species are oxidized and what species are reduced, your answers must be reactants. Giving an answer that's a product doesn't make sense. Be careful about that because that's a common error. So what we see is that the sodium is going from an oxidation number of 0 to +1, as we pointed out. Its oxidation number is going up, and therefore sodium is getting oxidized. Now I'm going to take this one step further. Let's write the half reaction for the oxidation of sodium. Sodium is losing 1 electron to make a sodium ion, so I've got a balanced half reaction for just the oxidation piece. The elemental bromine is going from an oxidation number of 0 to an oxidation number of -1. So the bromine is getting reduced. I do have to be careful when I write my half reaction that I show conservation of mass and charge. I have Br2 making 2 Br minus. that requires 2 electrons on the reactant side. The other thing I want to point out is that since I need 2 electrons to reduce Br2 to the 2 bromide ions, I need 2 copies of the sodium oxidation half reaction in order to write a balanced equation. Here's another example. What's oxidized and what's reduced? Work out the oxidation numbers, figure it out, and then listen to my solution. Now that you've tried it on your own, here are all the oxidation numbers: magnesium, copper, sulfur, oxygen on both sides. What we see is that the magnesium on the reactant side has an oxidation number of 0, but it goes to +2 in magnesium sulfate. So magnesium is getting oxidized. We can write the oxidation half reaction. Mg makes Mg2 plus 2 electrons. In terms of reduction, sulfate stays as sulfate on both sides, so I'm really not worried about the sulfur or the oxygens because they didn't change. It's got to be the copper. And we see that it went from an oxidation state of +2 in CuSO4 to metallic copper, which has an oxidation number of 0. And so the copper ion in copper-2 sulfate is getting reduced. And I like that phrasing because I'm being crystal clear what's happening. And then we can write the half reaction for the copper ion gaining 2 electrons to deposit as solid copper metal. There's one last thing I'd like to comment on about redox reactions in this webcast. We can say that the substance that gets reduced is called the oxidizing agent. By getting reduced, it makes it possible for the other species to oxidize. The species that gets oxidized can be referred to as the reducing agent. By getting oxidized, it makes it possible for the other species to get reduced. These terms aren't tested on the AP exam anymore. So why am I mentioning it? Because it's important in terms of everyday analysis. Substances that have a strong tendency to undergo reduction, for example, permanganates, are really strong oxidizing agents. They undergo reduction really well. They react vigorously with materials that can oxidize, and so it becomes a chemical storage issue. And so I wanted to point that out. So if we go back to our sodium plus bromine reaction that we looked at before, we know that sodium gets oxidized in this reaction and bromine gets reduced. Therefore, we can state that sodium is the reducing agent and bromine is the oxidizing agent. In the reaction between magnesium and copper-2 sulfate, we know that magnesium gets oxidized, the copper ion in copper-2 sulfate gets reduced, and therefore we can state that magnesium is the reducing agent and the copper-2 sulfate is the oxidizing agent. Just to wrap up with a short summary, remember, oxidation is a loss of electrons, and reduction is a gain of electrons. Those 2 mnemonics, Leo's line says "gur" or oil rig, can help you to keep those definitions straight. We can represent these with half reactions. We know that redox reactions involve changes in oxidation numbers. I hope you found this helpful. Subscribe to my channel so you get all my latest videos. Like the video and leave a comment. Practice chemistry every day. That's how you get better.